The phrase functional programming can mean different things in different contexts. As we've used the phrase, we mostly meant it in the sense of avoiding state. That is, if we have a notion of a shape and a scale function that takes a shape and an amount to scale it by, then we get back a new shape. It doesn't change the shape S. Here I've made a shape R for a rectangle. Its area is 150. When I scale it, I get a rectangle that's much bigger, but that doesn't change R. In this sense of functional programming, the alternative would be imperative programming. That is something that changes the state of the shape S, and so that it actually changes R instead of getting back a new shape. But there are other senses that people mean. Sometimes when people say functional programming, it's more about using functions as values to implement different programs. For example, here I'm using a function that takes a shape S and checks whether its area is greater than 40 and passing that into map to work over a list of shapes. The alternative here would be perhaps procedural programming, something like C, where you don't have function expressions that you can nest and capture variables from the lexical environment. But there's one more sense of functional programming, and often this use of the word functional programming might be better described as data type-oriented programming. That is, when we want to represent a shape, we write a type form with these three variants here: rectangle, square, equilateral, triangle. And then we write different functions that each match over those different possible shapes. So every function that we write matches the shape of our shape definition, or in general our types. And that is a data type-oriented programming, which is typical of functional programming. We do the same thing with lists. A list is either empty or cons, and so when we write a function that processes lists, then it matches on those two possibilities. In this sense of the phrase functional programming, the alternative is object-oriented programming. And that's because in data type-oriented programming, we build our programs around these individual functions, each of which implements a separate operation and has to consider all the variants. In object-oriented programming, we organize our code around the different variants, each of which implements the different operations that apply to that variant. The effect of this difference in style is that with data type-oriented programming, when we want to add a new operation, we just add a new function. So we can add a function scale here for shapes without changing the area or perimeter functions. On the other hand, when we want a new variant, like let's suppose we want to add support for circles, we have to go change all of our existing operations, all of our existing functions, to add support for circles. In the object-oriented style, every time we want a new operation, like a scale operation on shapes, we have to go change all of our existing variants to add the new operation to them. On the other hand, when we want a new variant, suppose we want to add a circle variant, then we just make a new class and we don't have to change any of the others. So there's a real trade-off between these two choices of organizing things around the operations versus organizing things around the variants. These are different programming styles, not necessarily different programming language constructs, but different programming languages offer constructs that make these different styles more convenient or not convenient. For example, Shplait offers type definitions and match, so it makes data type-oriented programming easier. But we can make our way to object-oriented programming and eventually look at what a more object-oriented Mo language would look like.